Good afternoon, everyone, and welcome to today's sponsored ABC webinar, Addressing Feedstock Challenges in Anaerobic Digestion. My name is Caroline Pete, and I will be facilitating this webinar. First, I want to give a big thank you to EconWord for sponsoring today's webinar. Their sponsorship directly supports ABC and its programs. And before we begin, I just want to go over a little bit of housekeeping here. You should be able to see the slide titled Quick Notes. If you're hearing echoes or your sound quality is bad, you can change your audio input using the audio pod on the GoToWebinar toolbar, which is on the right side of your screen. And if you're still having trouble, at any time you can send the organizers a message using the questions pod there. We'll be able to help you throughout the webinar. And if you're still having problems after that, don't worry, we are recording the webinar. The recording and slides will be sent to all registrants after the event. If you have any questions about the content, you can ask those at any time too. We will be handling the questions most at the end of the webinar with all of our speakers. If you're on mobile, that questions pod is in the upper right-hand corner of your screen. It looks like a little question mark bubble. EconWord has also provided handouts for you today. So if you see that handouts tab in the GoToWebinar toolbar, you can view those there. We'll send those out as well after the webinar with the recording. And with that, I'd like to hand things off to Joe Ayala, who's our moderator and one of our speakers today. And he's going to lead us through the great presentation. Joe, the floor is all yours.
Thanks, Caroline. My name is Joe Ayala. I am the COO, Chief Operating Officer for EconWord, responsible for the North American market. And I will hand over this wonderful presentation to my colleagues, Mackenzie and Jessica.
Hello, I'm Mackenzie Bernhardt. I'm the sales engineer here at EconWord.
Hi, I'm Jessica McWilliams. I'm the business development manager for North America.
All right, and we're also going to turn off our cameras just for bandwidth purposes, so hopefully we don't lose you guys throughout the presentation, but we'll get it going. So good afternoon, everyone. Today, we'd really like to take some time to discuss a pressing issue in the field of renewable energy. Specifically, we're relating this to the scarcity of feedstocks and anaerobic digestion. We're particularly focusing on municipal solid waste, or MSW for short, throughout this webinar. But as we continue to seek some sustainable solutions to our energy needs, understanding this challenge is crucial. And just as a little disclaimer, this presentation is not geared towards agricultural feedstocks, but rather to new feedstocks outside that agricultural sector.
Okay, here we will discuss a few of the key challenges and innovative solutions needed. One of the primary challenges that we face is the increasing competition for organic materials for anaerobic digestion, which are resulting in lower prices per ton. Our good feedstocks, such as pure pre-consumer food waste or source-separated organics with low levels of contamination, they're being less and less available due to the increase in competition. The tipping fees paid by the seller of clean organic feedstocks for an anaerobic digestion, they'll continue to decrease due to the increasing demand from biogas developers seeking long-term contracts. So these plummeting tipping fees make biogas projects harder and harder to cash flow. Additionally, the complexity of processing MSW poses yet another hurdle. Effective separation of the organic fraction from the non-organic material is absolutely crucial for ensuring that the feedstock quality remains high. Without adequate sorting, the operational efficiency of the anaerobic digestive system can suffer, ultimately reducing biogas yield and undermining the potential benefits for anaerobic digestion. Currently at this time, there aren't many successful examples of a stable biogas production from highly contaminated organic rich feedstocks like our MSW or material recycling facility rejects. And anaerobic digestion of highly heterogeneous feedstocks is already extremely complicated, and it increases the project risk. So to address these challenges, innovative solutions are absolutely necessary. First, advanced sorting technologies will play a vital role in improving the efficiency of separating biodegradable materials at a material recovery facility. By enhancing the separation process, we can ensure that a higher quality of feedstock is available for digestion. Moreover, integrating anaerobic digestion with other waste management strategies can greatly enhance feedstock availability. For instance, combining anaerobic digestion with composting and other recycling methods can optimize the use of organic materials, thereby supporting a more circular economy. This holistic approach not only addresses feedstock scarcity, but also contributes to a broader sustainability goals. As the demand for renewable energy continues to rise, tackling feedstock scarcity through innovation in waste management practices is essential for us. By doing so, we can not only meet our energy needs, but also contribute to a more sustainable future by minimizing waste and enhancing resource recovery. Next slide, please.
So as Jessica mentioned, as the demand for these biogas projects grows, reliable feedstock availability is becoming a limiting factor for expansion, which is really making it crucial to understand where feedstock comes from and what untapped sources exist in the marketplace today. So first, we'll start by examining the image on your left, which shows a breakdown of biogas capture systems across the US according to feedstock sources. Here we see a range of feedstock types like wastewater treatment plants, landfills, agricultural byproducts, and food waste. Traditionally, wastewater treatment and landfill biogas systems have been dominant, and these sources provide the backbone for our current biogas production infrastructure. That green waste, which is typically dry digested with lower biogas yield, and then dairy ag waste is digested wet and has a high biogas yield, and it has consistent composition. Food waste is a smaller contributor at this time, but they're highly valued due to the high organic content, which will then generate more biogas per unit volume. However, these resources are really limited. They're super geographically dispersed, and they're often hard to collect or pre-treat, all of which contribute to a constrained feedstock supply chain. If we draw our attention now to that image on the right, we get a view of the untapped feedstock sources that could potentially support biogas projects in the US. These include additional food waste from commercial and industrial sectors, or like pre-consumer food waste, agricultural residues, and the organic municipal solid waste that's still largely landfilled to this day. That 20.6% of green waste really should be used for composting, as it's less valuable to pencil down with some of these anaerobic digestion projects. The 12% food waste is projected to decrease in coming years, as that public and private sectors are really trying to improve the utilization of food, and there's more competition from biogas developers for this feedstock. For this reason, that price per ton is really going to decrease significantly when you're bidding on projects. The 3.8% biosolids are projected to increase, but that's going to be tackled by public wastewater treatment facilities. Also, don't let that small percentage fool you either. That's still around 7 million tons of feedstock annually in those biosolids category. The capacity of those plants too is really large, and a huge percentage of availability is still left for co-digestion at those wastewater treatment plants. The large green region you see at the bottom there represents 63.7% MSW, or municipal solid waste, which will increase with population. And the more we try to recycle, the more contamination is going to end up in that waste stream. That OF-MSW, or organic fraction of municipal solid waste, accounts for food waste, paper and cardboard, and those minimal yard trimmings that are produced at the household or residential level. And that accounts for well over 100 million tons produced annually. While these untapped resources are super abundant, factors like those collection logistics, contamination, and regional variability make capturing them a complex challenge. With our know-how here at EconWard, processing this MSW and treating it at new biogas sites or existing wastewater treatment facilities, due to our co-digestion patent, is now possible. So really together, these images are highlighting both the reliance of the biogas industry on established sources and the need for new sustainable feedstock avenues. Right now, it's estimated that there's still over 15,000 potential sites to include biogas infrastructure, meaning the untapped potential is nearly 10 times larger than most of that potential comes from the organic fraction of municipal solid waste, as we can clearly see above. To address these feedstock scarcity, biogas projects must innovate in feedstock sourcing. They need to collaborate across these different sectors, and they need to look into new collection strategies to make use of these underutilized organic materials. Solutions to these challenges will be vital for the growth and sustainability of the biogas industry as we continue to push for a cleaner and more circular economy. Next slide.
The organic fraction of municipal solid waste, or OF-MSW, is considered one of the largest untapped feedstock for anaerobic digestion for several reasons. To highlight a few, the US generated approximately 63 million tons of food waste annually, of which a significant portion ends up in our landfills. Most of the waste is part of the organic fraction of MSW. Diverting it from landfills to anaerobic digestion plants could dramatically increase biogas production while reducing our greenhouse gas emissions. A large share of this waste is not yet being captured for anaerobic digestion, presenting a massive opportunity for us. Globally, about 1.3 billion tons of waste is wasted every single year, with a significant amount being organic waste that's either disposed of in landfills or left completely unmanaged. If even a fraction of that waste could be used in anaerobic digestion plants, it would provide a sustainable, renewable source of energy. Europe in particular has been leading efforts in integrating OFMSW into energy generation, but the US and other regions have lagged in fully harnessing this resource. Our cities and states are increasingly adopting zero waste initiatives and landfill division mandates, especially the organic materials. For instance, California's SB 1383 laws require a 75% reduction in organic waste by the year of 2025, creating a larger incentive to use OFMSW in anaerobic digestion plants. Yet, many jurisdictions have not fully implemented systems to divert this feedstock to anaerobic digestion facilities, leaving it underutilized. In countries like the US, where landfill tipping fees are high and regulations are tightening, there is an economic case to be made for redirecting OFMSW to anaerobic digestion. Not only would it reduce landfill costs, but it will allow municipalities and private companies to generate revenue from biogas and digestate products, such as fertilizers or soil conditioners. For example, a single AD plant processing OFMSW in the UK was reported to produce enough biogas to power 12,000 homes. Our new technologies, such as Econ Ward's Biomax system, are being developed to efficiently process OFMSW for anaerobic digestion, offering scalability and adaptability to different waste streams. These innovations are making it feasible to process OFMSW in regions where traditional anaerobic digestion systems have struggled with contamination in the past or ineffective feedstock separation. These examples demonstrate that while OFMSW is abundantly available, it remains underutilized in many regions, offering a significant opportunity for expansion and anaerobic digestion capacity globally. Next slide, please. As we face increasing scarcity of high quality, clean organic waste for anaerobic digestion, technologies like Biomac offer innovative ways to transform a broader range of waste materials into viable feedstocks, increasing biogas production potential and improving efficiency. The Biomac system uses a process known as thermal hydrolysis, which acts like a pressure cooker in our kitchen. It applies temperature and pressure using saturated steam to break down complex organic materials and waste. This breakdown produces results in simpler, smaller molecules such as sugars, fatty acids, and amino acids, as shown here in the hydrolysis section of this slide. By converting carbohydrates, fats, and proteins into the simpler components, Biomac enables a higher biogas yield when the material is fed into the AD system. One key benefit to Biomac is the separation of the organic stage from the AD process itself. By doing this, Biomac helps treat plants and conditions the feedstock, making it more readily digestible for microbes in the anaerobic digestion system. This not only increases biomethane potential, but also reduces the residence time in the digester, meaning faster, more efficient biogas production. This pre-treatment step is particularly available for materials that are typically harder to digest, such as municipal solid waste or contaminated separated organics and material recovery facility rejects. As shown on the slide, biomass can handle multiple types of waste feedstocks, including food waste, green waste, residuals with high organic content, and compostable or biodegradable materials. This versatility allows biomass to process a diverse range of waste types, broadening the feedstock basability of anaerobic digestion facilities. By utilizing biomass, facilities can turn what might be challenging low-quality waste streams into high-value feedstocks, thereby addressing one of the main hurdles for anaerobic digestion projects: feedstock scarcity and variability. Finally, the output from biomass thermal hydrolysis processes a uniform, pathogen-free, chemically degraded biomass. This resultant biomass is not only physically degraded, but also safer for handling, as pathogens are neutralized during the hydrolysis stage. The pre-treatment also creates a more homogeneous feedstock, which further optimizes the digestion process, making it suitable for various downstream anaerobic digestion processes. Biomass offers a powerful solution, you guys, to a challenging feedstock scarcity and quality in anaerobic digestion projects. By pre-treating diverse waste materials and enhancing their digestibility, biomass maximizes biomethane production potential while reducing overall process time. This innovation can help the anaerobic digestion industry adapt to the changing landscape of waste management, making it more suitable and resilient. Next slide.
So this slide shows short clips from a video rendering that demonstrates biomass capabilities in a more illustrative manner. The original version of this deck has the full video, but we'll just show a breakdown of clips just for those bandwidth purposes. But if you're interested in seeing these full videos, we're happy to share them with you following this webinar. So our system consists of 4 autoclaves connected in series by means of hydraulic valves. Inside, the waste is subjected to thermal hydrolysis. The top inlet hopper has a scale for precise weighing of incoming material before it's fed to the first autoclave. Once the first autoclave or that inlet chamber is loaded, the hydraulic valve is closed and saturated steam is injected until the desired pressure and temperature conditions are reached. That pressure can range from about 29 to 58 psi, and the temperature ranges from 248 to 320 degrees Fahrenheit. The main purpose of the valve is really just to balance the system pressure in the most efficient way. Next slide. After reaching the parameters set by the operator, the inlet valve to the second autoclave is opened, allowing the material access. The second and third autoclave, they're called the reactor and the transit chamber respectively, rotate that internal material. At this point, a new batch of waste would then enter that inlet chamber, but just for the sake of understanding visuals, this rendering just follows one particular batch of waste. Next slide. Thanks to this movement and the stability of the preset temperature and pressure conditions, we can really guarantee an effective and efficient thermal hydrolysis. This thermal hydrolysis process ensures a homogeneous, degraded, and hygienized biomass. These 2 chambers, like I had said, the reactor and transit chamber that are shown in blue here, operate continuously and are always conditioned at the same high temperature and pressure conditions, regardless of where those other autoclaves are in the process. Next slide. This rendering here just shows the hydrolyzed material entering the transit chamber, and this is done just to really ensure a full hydrolysis and undergo a longer residence time in these conditions while still being able to maximize the use of the autoclaves at this time. Next slide. Finally, in this 4th autoclave or the outlet chamber, the depressurization takes place to unload the material at atmospheric pressure. The system is synchronized to reuse the steam from the depressurization for a new inlet chamber pressurization process. That system there is bidirectional, which allows for the balance of both pressure in both chambers. In that last chamber, the material is transformed into our biomass, which will be transported to a post-treatment process by way of conveyor belt system and through a mechanical separation. This mechanical separation is done through a vibrating screen where the hydrolyzed organics fall through a 40mm sieve screen, and those non-organics or the overs are carried into a separate collection bin. The time required to obtain the biomass is 40 minutes from the time the waste is placed into the receiving pit, but it undergoes hydrolysis in 20 of those minutes. Next slide. So this process flow that you see here is going to appear on the next few slides as we dive into some better footage of the biomax system taken at our full-scale operational facility in Madrid, Spain. Like I said before, the original version and the presentation that we're happy to share with you guys has better videos of this, but due to the bandwidth and the turnout of this webinar, we're just going to use screen clips from those videos to be sufficient in the meantime. Next slide. So really starting from square one, this is what the tipping floor looks like on an average day. Most of this composition is MSW, but you can see some areas where the load is more consistent with materials recycling facility rejects, but all of that's totally fine since the material entering that inlet hopper has just the sole criteria of being under 10 inches. So any form of that mixed residential waste is completely accepted and is commingled. Next slide. So this slide shows the first step of the process flow diagram from a different view of that input waste getting dropped in the hopper, where we'll undergo a magnetic separator before entering the biomac at about 8.8 tons per hour. Next slide. This one just shows a sample of that same waste just to really get a preliminary visual of what that waste will transform into. With that in mind, please pay attention to those purple plastic bags because you'll see them on the back end as well. Next slide. This is that hydrolysis stage, which is that 4-step autoclaving process from the biomac. The picture from this video shown is one of the open autoclaves from one of our trips to Rivas, which is that operational facility in Madrid. Jessica and I actually had the operators open up the autoclave to really prove that that system yields a pathogen-free biomass. If there were still pathogens or any of that foul bacteria, the steam would smell and it would leave you and your clothes covered in those trash smelling particles. But instead, it kind of smelled like a baseball field, like after a rainstorm, where it's really just that clean dirt smell. Next slide. So this is just a sample of that hydrolyzed biomass before separation. If you look close, you can kind of see those purple trash bags are all hardened and shriveled up. Since the system reaches a high enough temperature to shrink and harden the plastic, but not hard enough to really melt it. You'll kind of see those out on the outskirts or up in the middle where it looks kind of like just shriveled up plastics. Next slide. So this slide shows the flip flow vibrating screen at a 40mm sieve size. Unfortunately, this video really should be shown like as a video, so you can kind of see the way that the separation is taking place. But all those clean inorganics bounce over the screen and into a bin of mixed clean inorganics that can be further processed with other sorting mechanisms. And the organic fraction is now physically and chemically degraded and falls under those sieves into a bin of the hydrolyzed biomass. Next slide. This rendering just shows those clean organics with minimal contamination. From here, you can further polish and get rid of those like very few heavy and light residuals like broken glass or microplastics that might fall through those sieves. Next slide. But this is just what that fraction looks like. It's almost mulch-like. Like you can pick it up with your hands. It's relatively dry fraction. It gains about 3 to 5% moisture content from the original state pre-hydrolysis. And that's because steam's being injected and recirculated through the system and not liquid water itself. It's just steam being injected. Next slide. Similarly here, we have that non-organic fraction that we discussed earlier that's now pathogen-free and clean of all those organics. After further separation, the plastics and other valuable material can be turned into refuse-derived fuels or it can just be recycled. In the absolute worst case scenario, only a small portion of this waste is now landfilled as opposed to that entire load that we saw on the tipping floor being landfilled. Next slide. Just like before, here's a sample of that fraction where you can really clearly identify those Coca-Cola cans from the water bottles, from the sticks, and all those other inert materials. They're easily identifiable. Next slide.
Okay, now let's dive deep into the separation capabilities of the biomax system's high efficiency organic capture process. Starting with the incoming mixed waste you see here, which is about 58.9 organic, Biomac applies thermal hydrolysis to separate the organic materials from the non-organic contaminants. After hydrolysis, the material is processed on the flip flow screen, which removes larger organic items known here as the rejected materials with a rejection rate of about 90.5% non-organic. The remaining materials undersized to below 40 millimeters is 83.2% organic. As a result, biomass just captured 96% of available organics, producing a cleaner, concentrated biomass ideal for anaerobic digestion. This process maximizes organic recovery, enhancing both efficiency and yield for biogas production. Next slide. This slide highlights the biomass system specification and operating perimeters. Biomass is designed for high capacity, handling up to 8.8 short tons per hour, or about 70,000 tons annually, all within a compact 3,000 square foot footprint. It processes high solid organic fractions of municipal solid waste, with total solids ranging from 20 to 70%, making it versatile for a variety of waste inputs. On the right, we see the system's core, 4 autoclaves operating at 150 degrees Celsius with 4 bar pressure. This high temperature and pressure setup ensures rapid thermal hydrolysis, with a total residence time of just 20 minutes, opposed to the 7 to 10 days biological hydrolysis that happens in anaerobic digestion systems. Biomass' robust, compact design makes it reliable and ideal for facilities looking to maximize space and throughput in organic waste treatments. Next slide. As we come to the conclusion of our presentation, let's go ahead and recap the significant economic and benefit and environmental benefits of biomass. The innovative approach not only transforms how we manage municipal solid waste, but it also presents a substantial advantage for both jurisdictions and developers. For developers, biomass offers crucial cost savings, you guys. By diverting organic waste from landfills, municipalities can now significantly reduce their budget burdens, including lower landfill tipping fees and decreased transportation costs, all while processing waste locally. This shift assists jurisdictions in meeting regulatory mandates and avoiding potential fines related to organic diversion laws. Moreover, biomass promotes reducing landfill dependency. With less organics heading to our landfill, there is a corresponding decrease in methane emissions, which we all know are harmful to our environment. This reduction not only mitigates climate impact, but also extends the life of the existing landfills and delays the need for costly expansions. Now, let's turn to the benefits for our developers. The most notable advantage is revenue generation. Developers can monetize previous untapped organic waste streams now, such as the organic fraction of municipal solid waste to produce biogas. This not only provides a new revenue source, but it also supports the growing demand for renewable energy. Additionally, developers can sell byproducts like nutrient-rich digestate, promoting sustainable agriculture while participating in a circular economy. This aligns with the increasing customer demand of environmental friendly products and practices. Biomass represents a transformative solution for both waste management and sustainability. By addressing economic pressure and environmental concern, we can now create a system that benefits our communities and supports a healthier planet. Next slide.
As we wrap up our presentation here, let's just take a moment to reflect on the critical role that biomass plays in addressing these feedstock scarcity issues and promoting sustainability within anaerobic digestion processes. This innovative solution is not just really about waste management, it's about transforming how we think about organic materials and energy production. Biomass serves as a key solution for the growing challenges we face in managing municipal solid waste. By efficiently processing organic waste, biomass helps reduce landfill dependency while generating renewable energy. This process aligns with our global sustainability goals and contributes to mitigating climate change by reducing greenhouse gas emissions, particularly methane, which is then released from landfills. In essence, biomass stands at that intersection of waste management and renewable energy. It provides a pathway to repurpose organic waste, turning a potential environmental liability into a valuable resource. That dual benefit is essential for creating a more sustainable future. But let's talk about how you can get involved here. Our call to action really emphasizes the importance of leveraging biomass in your anaerobic digestion and waste processing projects. By optimizing the use of biomass, you can maximize feedstock utilization, reduce operational costs, and significantly contribute to sustainable waste management practices. Let's first dive into optimizing your projects. You can use biomass to enhance your current waste processing operations. This can involve integrating advanced technologies for sorting and processing organic waste, thereby improving the efficiency and increasing your biogas yields. We're also going to maximize feedstock utilization. Let's identify and tap into those underutilized organic waste streams within your communities or business. That really is just your MSW, that municipal solid waste. Properly channeling these materials into the biomass process not only provides the necessary feedstock for anaerobic digestion, but also reduces the amount of waste that we're sending to the landfills. What we're really here to talk about too is reducing those costs. By diverting your organic waste from landfills and generating renewable energy, you can significantly lower costs associated with waste disposal and energy procurement. This economic incentive can really help bolster your bottom line when you're advancing your sustainability initiatives. All in all, we're contributing to a sustainable future. Ultimately, by embracing innovative waste management solutions like biomass, you're making a commitment to a more sustainable future. This not only benefits your organization, but it has a positive impact on the environment and your communities. Overall, biomass is more than just a waste management solution. It's a catalyst for change in how we handle organic materials and generate renewable energy. As you consider the next steps for your project, remember that leveraging biomass can lead to significant economic and environmental benefits. Next slide. Here at EconWord, we're so proud to have solved those issues of corrosion abrasion for continuous autoclaving of solid waste. With this technology, we have significant impact on current and future operations. We hold ISO 9000, 14000, and 45000 certifications, as well as a certification on all of our production values. We've developed over 4,000 blueprints, 1,500 technical documents. We hold multiple patents and significant trade secrets on the field of continuous autoclaving of solids. As I previously mentioned too, we've also just been granted another co-digestion patent, which will expand and tap into that open capacity at wastewater treatment plants with our hydrolyzed organic fraction. I just want to end this all by saying thank you so much for your attention, and we welcome any questions or discussions on how we can collaborate these initiatives. I'm going to pass it off to our COO, Joe Ayala.
Thank you, Mackenzie. I will address the questions now. We have a bunch of very, very good questions. Thank you, Mackenzie and Jessica, for the presentation. I'll start from the top. The first question, Nicholas Wilson talks about, seems to be a good opportunity. Thank you, we agree with you. And he wonders why, how can other countries like Denmark deal with this, and we cannot. The difference is that the population of Denmark is about 5 million, give or take. That is, I live in Los Angeles, so that's equivalent to a little piece of Los Angeles. The difference between LA and Denmark is that the population density in Denmark is 135 people per square kilometer versus 2,900. So it's like 135 to 3,000 people, the difference, right? So it's about population density. And what happens is that humans, when they are together, creates a lot of waste, and that waste contains a lot of organics. So the answer is population density. That's why, because we have massive cities that keep getting bigger, and the waste problem, the organic content in municipal solid waste keeps increasing, and it's just gonna keep increasing. Rafael Sanchez asked about the sulfur content. It is reduced when we hydrolyze the biogas feedstock. We reduce, so that typical H2S content for a biogas plant is 2,000 or 3,000 ppm, and we can lower that significantly to 500 or 800 ppm. So it's a significant decrease. in H2S generation within the biogas. So that's an advantage. Recording slides, yes. Javier Duarte, yes. There is a comment here from Bernard Fenner about SB 1383, the law of the land here in Los Angeles, in California, and how, you know, he talks about the challenges to implementation. That's true, and that happens all over the world. Our view and our vision is that we should do everything we can to divert organics from landfills. Yeah, landfills and landfill gas collection systems are a stopgap measure. It's something that we are doing now to make the problem smaller. But to stop that from happening, we think that diverting organics from landfills and sending it to anaerobic digestion is a much better solution, much cleaner. And also is better in terms of economic viability long term. Rafael asked about digestate production. That is a good question. We produce much less digestate because we are fully cooking the feedstock that produces less digestate. Does increasing biogas production pays for the technology? We need to do a cost-benefit analysis, but the short answer is yes. The short answer is because we have developed this technology that can pre-treat the biogas feedstock. And we not only are going to produce more biogas, we're going to produce more methane in biogas, and we're, instead of taking, say, 30 days residence time in the digester, it's going to take only 20, so that increased capacity of the digester, and it's going to produce less H2S, so you're going to need less cleaning systems, scrubbing, and because also this enables the diversion from landfills, you are going to save on the landfilling fee, and you won't have to build infrastructure at the landfill now. So this, from a carbon footprint perspective, from a decarbonization perspective, this is one of the best options that we have. It's an innovation, it's something new, but it's a very, very good option, and it makes a lot of economical, financial sense. Bill Alhaus asked about the energy value chain. Thank you for the question. It's 1 to 7. So for every unit of energy, for every MMBTU that we will spend pre-treating and digesting this feedstock, we're going to produce 5 to 7 units of energy. So it's a very, very, very good energy value chain. Good question. What kind of chemicals are used in the biomass process? The only chemical that we are using is called H2O, is water in the form of steam. That's all that we use. And at that, a very, very low pressure. Think of 30 to 50 or 58 psig, very, very low pressure. So this machine treats the feedstock very quickly at very low pressure, kills all the pathogens, and cooks all of the feedstock. So the net result is that the carbs, the carbohydrates, become sugars, the fats become fatty acids, and the proteins, the meat, becomes amino acids. For instance, in the pictures that Mackenzie show in the slides, what you see, the captured organic fraction, the hydrolyzed biomass that we call it, out of the flip flow screen, the Anders, what you are seeing there is sugars, fatty acids, and amino acids. That's exactly what you are seeing. Are there captured nutrient-rich? So the question from Ed Weisenberg, are there captured organics nutrient-rich in nitrogen, phosphorus, and potassium? Yes, of course. It will conserve all the nutrients, right? We are not destroying the nutrients with this slow cooking, this pressure cooking that we do. Not slow, it's very quick, it's 20 minutes. Where do the pollutant microplastics end up? In you. So when you eat a lettuce from a bag, and the microplastics that are in the lettuce, even if you wash it or even if you steam it like we do, they will end up inside the human body. The same for this. Our process doesn't have high enough pressures or temperatures to destroy, because it will also destroy all the biogas value if we were to do that. So those nanoparticles, we need to stop them at the source. This machine is not going to do that. What is the height of the 3,000 square foot facility? Is about 60 feet. So it's tall. Jennifer McDonald, is the material delivered to the digestion site a liquid or a solid? It's a solid. It's a solid that the hydrolyzed biomass composed of mostly sugars, fatty acids, and amino acids. It's a solid. It's a solid with 60 or 70% or 80% humidity, but it's a solid. We don't like tracking water. Yeah, so this enables that. So it's a huge reduction, and this represents a step change in terms of a pretreatment method that can be located away from the anaerobic digestion facility, because transport is very cheap, because we are not moving water. For you to have an idea, we have a project here in LA that in theory necessitates 700 tons of this liquid feedstock. If that was hydrolyzed biomass, it would be only 100 tons, right? So it would be 2 or 3 trucks instead of 20 or 30. Yeah. So we are reducing the transport cost significantly. Ed Weisenberg, who else besides byproduct? So I think he's talking about using the digestate, use of the digestate. Our digestate, because it's the output of a certified process, can be certified for land application and use as a fertilizer. That issue doesn't have anything to do with PFAS or microplastic. That's a different story, right? And it's a story that is going to impact us all. Is there any concerns with the chemical contamination carried over? That's a very good question asked by Jörg Blitzky. The question is very good, and the answer is no, because most of the contamination is not in the organic fraction, is in the non-organic fraction that we send for either further recycling or landfill in the worst case scenario, because what we are trying to capture is the organic fraction. Yeah. Accelerate the corrosion. This is a very good question about Peter Waters. That's asking whether the presence of fatty acids, which is very good, you got it, will accelerate corrosion. And yes, it does. So much so that it stopped this technology for all this time. This technology, people came up with the idea of using autoclaves in the 60s for or the 70s for all type of things, right, including waste. The reason why this hasn't been done yet is because resolving the issue of corrosion took all of this time, and we have done it, and we have patented, and we have a lot of intellectual property around that. Very good question. Thank you, Peter. Lots of questions coming. How much energy input? 1 to 7. We answer that. After hydrolysis, is the product always in solid form? Yes. David Henry, incoming MSW, what kind of pretreatment is done? We usually get rid of the bulk materials of the toilet wrapped in the blanket type of thing. We get rid of that. So we usually take a minus 10 or minus 15-inch fraction that we bring in. So usually some type of tromelin or bulk removal. This is not to process furniture, right? Consumption, we talk about that. The energy consumption per ton, it varies with the feedstock, but we can give you the cost. The total cost of pre-processing is $3 or $4 per ton. So it's very, very low in California, which is the most expensive in the country. Are there any sampling reports, yes. Conward team, do contact us if you have questions for us. All our contact details are in the slides. Are there any, currently operating plans? Yes. Our flagship operation is in Madrid, Spain, and we are always happy to take clients to see it. PFAS, we don't remove PFAS. We don't have enough pressure and temperature. That is a different problem. We are talking about capturing the organic fraction of municipal solid waste and use it to produce biogas. How should companies partner with you? Call us. Any experience with agricultural fibrous material? Yes, we do. We do have a lot of experience with that. And like Mackenzie said, this is not geared toward the agricultural sector because we don't need it. We don't need to separate organics from something that is organic pure, right? Like agricultural waste. Based on your concerns, scarcity, opportunities, you see, we see a huge amount of opportunities. This for George, Brian Souza. Nicholas Wilson asked us, just how are we doing? How are we doing on time? Oh, we still have
got like 15 minutes.
Excellent. Just want to cover this again. Can the equipment process all compostable packaging? Good question by Nicholas Wilson. Thank you very much. Yes, this is the only piece of equipment in the world right now that can take compostable packaging and separate separate the plastic from the paper in that compostable packaging. Compostable packaging is going to increase. Its cost of processing is going to increase. And we are now talking to the producers, the manufacturers of this packaging, because we think they will be super interested in having a technology that can really remove compostable packaging from waste. So, and we believe there is a huge opportunity there. Together with paper, think of paper, think of soiled paper. Soiled paper right now, when it comes to processing, is sent to landfills where it is unsustainable. We can capture paper, we can hydrolyze paper and convert it into sugars, fatty acids, and amino acids. Soil paper, right? And so this is a very good solution, not only for compostable plastics, but also for soiled paper, which is an enormous problem. And as we get rid of plastic packaging in California, more paper packaging is going to come in, and that paper packaging is going to go to our material recycling facilities, and it's going to end up in our landfills. So hey, let's capture it. This technology is great for that. Jorge, thank you for your comments. Cost per ton, that's what I mentioned before. Sidik, manure, not for manure, my friend. Annette Scotto, how long have you been in operation? For about 4 years in Spain. We took our sweet time to deploy this into the market. We just wanted to make sure we had technology that we could back 100%. So the technology is a technology readiness level 9. Thank you, Annette, for that question. John Morgan, heating systems, steam. What heating system we use? We use steam for this, the same steam that we need to warm up an anaerobic digester. How many people are required to, Wesley McLeod asks, how many people are required to operate this equipment? I want to say none. I want to say if you put this equipment on the back of a material recycling facility, you don't need to add any personnel. It's fully automated. It's just a machine that you put it through. Think of another one of your pre-processing technologies. But yeah, we need to look into that. But it is made in a way that the control panel the control screens can sit with the control room that exists already at a facility. Will the process work as a pretreatment for lignocellulosic? No. That's agricultural waste. Bill Alhaus. Are the Ed Weisenberg, are there gaseous emissions? No, this is just a steaming. This is 30, if you put waste with 30 bars steam, you're just gonna get steam. What's the minimum size? We can process, minimum size, we can process 8 metric tons per hour per unit, per machine. So that's about 200 short tons a day or so, operating 24/7. The minimum capacity, call us and we can look into it. What we want is for it to make sense, right? For the project to make sense. For operating facilities, is a steam source from natural gas combustion or a blend of biogas? We never use biogas for our own heating needs because biogas is worth a lot of money. So we burn natural gas, but a little bit, not that much. What do you, Brian Baumgartner, what do you do with your condensate? Very good question, Brian. We generate a condensate, of course, because we have a heating system here. So the condensate is put back into the organic fraction, the separated organic fraction. We spray it on top of it. So we give, because it's rich, it's organic rich. Yeah, so we collect that. We have a vacuum condensate collection system that is ancillary to this, that is included with the equipment. Last 3 questions, unless you guys have some more. Christopher Harper, any recommendations for AD mixing systems? I don't know, my friend. This is, we are AD agnostic. You can use dry digesters or high solids or low solids. In the States, 99% of all new digesters are low solids for a good reason. They are economically viable. So I cannot tell you what type of mixing you need to use. Does the moisture content of the feedstock after performance so Dimitris Theodoridis is asking about humidity. So when the say the input feedstock comes with, say, 70% humidity, we will add 3 or 4 or 5% humidity to that. So it's going to end up with, if it was 70, it was 75% maximum humidity. So so steam is going to add humidity, the steam and the condensate that we threw back into it. So yeah, we're going to add some humidity, but we're not going to make it a liquid. We're not going to make it a slurry. We're not going to make it a solution because we don't want to move water. Yeah. Please send the link to the videos. We will do. And Caroline and the amazing American Biogas Council team, they will send you the handouts. Do contact us for the videos because they are way heavier to send, but they are fun to watch. Turn down ratio. We can run 8 tons per hour, Rafael. So you can use it for 10 hours a day if you have a little bit of material, or for 16 hours a day, you can use less. You can switch on and off this equipment every day. That is true, and nothing is going to go wrong with it. It's just an autoclave. How does your process compare with Cambi? Very good question. Cambi, for those who don't know, is a machine that uses thermal hydrolysis, uses steam for liquids, for biosolids. This is used in the wastewater treatment plants, not for in the biogas sector per se, but it's a wastewater treatment plant solution. And the big difference with Cambi is that we are high solids. We can get municipal solid waste in and hydrolyze drier biomass out. Yeah, this is not for liquid slurries like Cambi. And the energy efficiencies between these two systems, because remember that they're heating up a liquid, we are steaming a solid. So the efficiencies differences are huge, benefit our system. So this is very good. Our system is very good for treating and separating and capturing the organic fraction of municipal solid waste with this method. Cambi is for another thing. It's for biosolids. Think of the feedstock biosolids that happens in human waste in wastewater treatment plants. But thank you for the question. This is for Ed. Pilot scale demonstration, for sure. We have a mobile pilot scale unit here in the United States, or you can come to Madrid and look at the real thing. What is the max capacity of the system? 8 tons per hour per unit. You can put many more units. And I think that was the last question.
Just in time.
Excellent.
All right. Well, thank you all so much for joining. Thank you again to Econward for sponsoring today's webinar, and we'll hope to see you on the next one. Bye, everyone.
Thank you, everyone.
Bye. Thank you.